we are going to take a look at the forces concept questions and their explanations. The first question is, assume that a bowling ball were to be rolled down a perfectly flat hallway. Describe the motion of the ball as it rolls. Now, as we can see with this one, it's moving in pretty much in a straight line. So here we go in a straight line, and it's moving at a constant speed. The reason for that is all of the forces are balanced. So when you roll a bowling ball down a flat hallway or an ice hockey puck along ice, you're going to have no friction. Therefore, there's no forces to slow it down. And once it's going, there's no forces to speed it up. So you're looking at constant speed or constant velocity. So if you're at a stoplight, large truck rear-ends you like it did in the picture. Which one gets hit harder, the car or the truck? The correct answer from Newton's third law is that the forces are going to be equal to each other. It doesn't matter that the truck is big and the car is small. It doesn't matter if the car is stopped and the truck is moving, or if the car is moving and the truck is stopped. Anytime any two objects bump into each other, hit each other, push off of each other, there's going to be an equal and opposite force, which is what Newton's third law says. So now if a soccer ball is moving to the right at a constant velocity, and I give it a little kick, I give it a bump in the upward direction here, which way is it going to go? Well, it's going to be moving with a combination of the right velocity and now an upward velocity that you gave it. So it's going to be moving at an angle, and it's going to move at a constant velocity after the kick because there's nothing to slow it down. So just like the bowling ball rolling along the flat hallway, as long as there's no friction or anything to slow the soccer ball down, it's going to move at a constant velocity. It's going to move at a new constant velocity that's a little bit bigger than this one because it's got all this same speed, and now a little extra was added when you kicked it. But what if I've got a rocket ship? Now I'm not giving it a one kind of kick, I'm giving it a constant force upward. If I'm giving it a constant force upward, it's still going to maintain that speed to the right, which is why it's continuing to sort of move in that general direction. But the speed upward is getting more and more and more and more because I've got this net force. And if I've got a net force, that means it's accelerating in that direction. So it's accelerating upward, which means it's going to cover more and more and more and more upward ground every second that it's got this acceleration. So that's why it's going to be moving in a parabolic path, getting faster and faster and faster. What would happen if the rocket's engines turned off? Well, now with the engines turned off, it would have no net force, so it would move in a constant direction with the same speed. So constant velocity, constant direction. So if a ball is thrown straight up in the air, what forces are acting on the ball as it rises, reaches the top, and comes back down? On its way up, at the top, and on the way down, it's going to have only one force acting on it, which is the force of gravity. In this class, we only really worry about forces that are actually touching, so pushes and pulls and ropes and things of that nature. Only one force acts over a distance, and that's the force of gravity in this class. Now, there's electricity and magnetism, but that's not going to be affecting a rubber ball as it's thrown up in the midair. We're only really looking at gravity. So as long as it's in midair, gravity is going to be acting on it, up, down, and at the top. So if I push my car to the left, and I'm pushing it at a constant speed, that means there's no net force. No net force means that my pushing force must equal my friction force. No acceleration means push equals friction. Well, what if I'm pushing more than friction? So my force of push over here, my force of friction over here. If I'm pushing it harder than friction pushing back, then I do have a net force. Then push is bigger than friction. And if there is a net force means there is an acceleration. So the couch will get faster and faster and faster to the left. But what happens if I just stop pushing it then? Well, if I just stop pushing it, there's no more force of push. There's only the force of friction. That means it's not balanced at all. There is a net force and it's to the right. But if it's moving left, but the force is to the right, it's going to start to slow down. So if you push something to get it moving, but then you stop pushing on it and there's friction on it, it's going to slow down and come to a stop. Why is it that electrical lines, you can see that they're kind of bowed here. They're not straight across like in this picture. Why is that? The reason for that, and if you look at the write-up on all these answers, it'll show you mathematically what I'm talking about. But as the angle gets closer and closer to being zero, meaning that the lines are going to be flat, straight across, left to right, as that happens, they get closer and closer to horizontal, the tension in those lines has to get bigger and bigger and bigger until it would reach infinity. Because not only do you have to pull upward to try and lift these wires up, but you also are pulling horizontally, pulling them tight. That force would be immense, because even though it doesn't look like it, you have to remember these wires are made of heavy-duty copper and metal, and that means they are going to have some weight to them. And to pull that much weight that hard takes a lot of force. And what's going to end up happening is you're going to pull so hard that it's either going to snap the lines or it's going to pull them clean off the towers. And either one would be bad. So they actually leave this bowing here because to pull them tight would have too much tension, and it would just, engineering-wise, it would not work. How can you tell if there's a net force acting on an object? Well, if I'm pushing with the same force as friction, then that means they're equal to each other. No net force because no one's winning in this game of tug of war, and I've got a constant velocity. But if a friend comes and helps me push this car, so we have two forces of push, and that's bigger than the force of friction, then if we're going to have a net force, it's going to be to the left, and the car is going to get faster and faster. So how do you tell if there's a net force? If there is a net force, it's accelerating. If there's no net force, it's moving at a constant velocity. You and a friend are both ice skating, you push off of each other, what's going to happen? Well, we're going to assume that the lady here in the picture has less weight than the guy. So if that's the case, they push off. Newton's third law says if they push, doesn't matter if she pushes or he pushes, they're going to exert an equal and opposite force on one another. So let's assume that force is 100 newtons, just for easy numbers. 100 newtons pushing him is going to push him backwards. And 100 newtons on her is going to push her also backwards for her to the right. So he's going left, she's going to the right. But if he's heavier, 100 newtons of force is going to accelerate him less, because F equals ma. If the m is big, the a will be smaller. So equal force pushing each one. If he's heavier, his velocity will be a little bit less going backwards than hers, because his acceleration will be a little bit less during the push. So he will move away more slowly than she moves away. So those are all of the answers to the concept questions. Hope you understood. Let me know if you have any questions.